In this discussion, we're exploring VideoLISA, an innovative model for handling video segmentation based on language instructions. Unlike earlier models that focus solely on images, VideoLISA effectively manages the unique challenges posed by videos, where understanding both time and space is crucial. It employs a technique called sparse, dense sampling to ensure that it captures important details over time without overwhelming processing resources. A standout feature is its one-token seg-all method, which simplifies the segmentation process by using a specific token to follow objects through different frames. The model has been rigorously tested against various benchmarks, including a new one called ReasonVLS, and it has outperformed existing methods in tasks that require intricate reasoning and tracking. Despite its primary focus on video, VideoLISA also shows promise for image segmentation, marking it as a potential all-in-one solution for object segmentation guided by language. Method. The section opens by referencing various models and their performance metrics across different benchmarks. The acronym MEVIS denotes a particular validation measure, specifically for a dataset called Ref. Davis 17. The table data includes performance scores, like those from models named LISA 7B and VideoLISA 3.8B, indicating that different configurations yield varying results. The text introduces the one-token seg-all training objective, highlighting its role in helping the model learn mask associations over time. This method focuses on ensuring that the model maintains a consistent understanding of object segmentation across multiple frames. However, practical constraints limit the number of frames processed simultaneously. Too many frames can overwhelm the system with data, reducing efficiency. To enhance the model's ability to perceive long-term temporal context, different pooling strategies are tested. These strategies involve consolidating information from frames in a way that balances both spatial, related to image details, and temporal, related to time evolution dimensions. Specific approaches include pooling separately in these dimensions, experimenting with varying intensities at different speeds, and introducing a novel method referred to as sparse dense sampling. The findings suggest that this last approach outperforms others considered, confirming that pooling methods that compromise visual detail yield poorer results, especially for tasks requiring a high level of visual fidelity, such as video segmentation. The discussion transitions into the temporal association module, where different designs for tracking objects in video frames are compared. The common approach involves utilizing a pre-existing tracking model like XMEM, which attempts to maintain object segmentation across video frames. However, results indicate that this method performs poorly in contexts requiring nuanced video reasoning. The issue lies in the limited comprehension of video content by the language model, which does not fully grasp all frame interactions. The subsequent subsection discusses the ablation studies performed on the training data, depicted in a table. The initial observations indicate that training on image-only datasets can yield modest performance, but reveals weaknesses in video-based benchmarks due to a lack of temporal data. Conversely, video-only training significantly enhances performance on video tasks while negatively impacting reasoning capabilities. The most effective strategy appears to be combining both image and video datasets for joint training, resulting in superior outcomes across diverse benchmarks. Further exploration includes the impact of integrating visual question answering (VQA) data into the training regimen. Initially, adding image-related QA data results in a slight performance decline, but the introduction of video QA data leads to a marked improvement in reasoning segmentation performance, especially on certain validation sets like MEVIS. The balancing act between different training data sources highlights the complex interplay needed to optimize model performance effectively. In this continuation of the method section, we delve into key aspects of the model known as VideoLISA and its capabilities, focusing on language-instructed reasoning and its implications for video segmentation tasks. Dynamic video reasoning. The authors explore how video-based question answering (VQA) data can improve reasoning abilities. However, it can complicate multitask training, leading to varying performance levels across different benchmarks. The challenges of aligning various data types and tasks are acknowledged, pending future investigation. Qualitative results. Figures 3 and 6 and 7 illustrate the model's coherency in language-influenced reasoning. VideoLISA excels in segmenting video content based on intricate language instructions. The model showcases its versatility by demonstrating proficiency not only in basic object identification but also in understanding context, dynamic behaviors, and subtle distinctions in language prompts, whether referring to specific objects or analyzing temporal sequences. For instance, distinguishing actions like the object that moves fast versus the object moving faster in this video exemplifies its capability to interpret varying degrees of language nuances. The authors clarify that these qualitative results derive from the one-token segal approach without additional post-optimization, making these achievements even more impressive. Failure cases. To further understand the model's limitations, the authors analyze several failure cases documented in Figure 4. One instance involves a scene with a car crashing into a grocery store. The model mistakenly identifies an irrelevant object despite multiple prompt rephrasing attempts. This suggests that the underlying multimodal large language model, MLLM, may experience hallucinations, misidentifying objects based on learned patterns rather than specific video information. In another example, when prompted to identify the loser of a game in a video, the model struggles due to a lack of context about the game rules. Providing background information improves the model's performance, showing that while VideoLISA has advanced reasoning capabilities, it still relies heavily on explicit cues to produce accurate outputs. Furthermore, certain segmentation masks were noted to be of low quality, indicating areas for enhancement. Benchmark overview. The authors provide an overview of the Reason VOS benchmark in Figure 5, which showcases data statistics. This benchmark comprises 91 videos, each accompanied by mask annotations and textual descriptions, with both short and long query formats employed. A total of 458 augmented samples were achieved using a specific API to broaden the dataset. The query types are elaborated upon, distinguishing succinct object references from more complex reasoning tasks. As we transition into the experiment section, this detailed examination of VideoLISA's operational mechanics and its implications for video reasoning lays a robust foundation, eliciting anticipation for the experimental validation of these functionalities. Experiments. Experimental setting. The experiments employ various datasets tailored for segmenting both images and videos. The image datasets include well-known collections like AD20K and PascalPart, focusing on semantic and referring segmentation, as well as reasoning segmentation samples sourced from LISA. For video data, the model is tested on semantic video object segmentation and referring video object segmentation datasets like YouTube VLS. Careful implementation details enhance model efficacy. Utilizing a multimodal large language model, LLM, with 3.8 billion parameters, the authors employ a vision encoder and mask decoder. The model undergoes joint training across different datasets, optimizing training parameters like learning rate, weights for various losses, and batch size, leveraging substantial GPU resources to achieve efficient training. Comparison tables. 3 tables compare different methods across several benchmarks. Table 1 presents results for referring video object segmentation on Refer YouTube VOS and Refer Davis 17, highlighting performance metrics such as J and F scores. The method denoted VideoLISA 3.8b is noted to outperform many traditional methods without reasoning ability, showcasing the model's advanced reasoning capabilities. In Table 2, the evaluation on the MEVIS benchmark further underscores the superiority of the VideoLISA 3.8b configurations, which achieve significant improvements over existing techniques, illustrating effective handling of motion dynamics and the training approach's innovation. Table 3 discusses performance metrics on the Reason VOS benchmark, again revealing a state-of-the-art position for the VideoLISA models, demonstrating a consistent ability to surpass competitors across diverse tasks. Evaluation metrics. For evaluating image segmentations, the paper utilized metrics like generalized intersection over union, GIOU, while the video tasks applied J and F metrics, which assess region similarity and contour accuracy, respectively. These systematic evaluations reinforce the robustness and adaptability of the proposed model across different segmentation challenges. Evaluation on video tasks. The results validate that the proposed method demonstrates both competitive and superior performance across evaluated benchmarks. Particularly in Refer, Davis, 17, the model achieved state-of-the-art results, highlighting the efficiency of the model design, even against larger models with more parameters. The findings set up a narrative of consistent innovation in addressing segmentation tasks, establishing a strong foundation for the forthcoming conclusions. In this conclusion, we present VideoLISA, an innovative video-based large language model, LLM, aimed at enhancing language-instructed reasoning for video segmentation tasks. Our research introduces two significant advancements: the sparse, dense sampling strategy, which adeptly captures temporal dynamics while balancing visual details and context, and the one-token seg-all approach, designed for consistent segmentation across frames. Extensive ablation studies validate these design choices, reinforcing their effectiveness. The VideoLISA model excels in complex reasoning, temporal understanding, and object tracking, as demonstrated through our newly established ReasonVOS benchmark. Additionally, it shows impressive capabilities in image segmentation tasks, establishing it as a promising unified solution for language-instructed object segmentation challenges. Overall, the findings signify VideoLISA's potential impacts on the fields of video processing and machine learning, culminating the research journey presented in this paper.